So I'd like to talk to you about the law of cosines. Okay, law of cosines, you've probably seen it before. It looks like this. It says that if you have a triangle with sides A, with angles A, B, C, and then little a, little b, and little c as sides, then the following relationship holds. A squared equals b squared plus c squared minus 2bc cosine big A. Now, let's just take a look at the formula for a minute. What I want you to notice is this little over here, this little A over here is side A. And this big over here, this big A over here is angle A. So we know that the convention for labeling triangles is that if this is angle A in this corner, the side opposite that is called little a. So this formula means that whatever side you have here, it has to be opposite that angle. So I'll write it this way. This side is opposite this angle. And that's really important. And also what that means is that you kind of have options about how you write this. Just like you can write the area of a triangle formula 3 ways, you can write the law of cosines 3 ways. So you can write it like this. You can say c squared equals a squared plus b squared minus 2ab cosine big C. Or you can write b squared equals a squared plus c squared minus 2ac cosine big B. And again, I'm acknowledging the rule that this side and this angle are opposite each other. You do that, you'll be fine. You'll never get law of cosines incorrect. Okay. So sometimes in mathematics they talk about, you'll hear a teacher or professor say the idea of a desert island theorem, or desert island rule. Okay? And so it's sort of like a joke. It sounds kind of funny. So let's pretend we were going to Triangle Island. There's a place, Triangle Island, and you know when you get there, you're going to have to find lots of missing sides and maybe missing angles and so forth. So the question is, what tools do you bring with you? Right? So some people might say, hey, wait a minute. I think I'm going to bring the law of cosines. So that's something I'll bring with me. Okay? So you might also want to bring with you law of sines. Okay? Maybe area that we learned. K equals 1/2 AB sine big C. Let's start thinking about some other theorems we might want to bring with us. Yeah, maybe someone might want to bring Pythagorean's theorem. Okay, now, once you create a list of things you think you might want to bring with you to Triangle Island, which is a ridiculous place anyway, but you can laugh about that, right? The question you should ask is, do I really need all of this stuff? Do I have to write all this stuff down or not? So I'm going to take a look at law of cosines for a minute, and I'm going to ask you to think about something. What if angle A equals 90 degrees? Let's just think about that question for a minute. So what would that mean? What it would mean is that my triangle would look like this. Here's angle A at 90 degrees. Here's B and C. I would start subbing into the law of cosines, right? So what would it tell us? It would say that A squared equals B squared plus C squared. Here's little c, here's little b, minus 2bc cosine 90 degrees. Cosine 90. I'm looking at that, I'm thinking, hey, wait a minute, I know what that equals, right? Yeah, cosine 90 is 0. So this piece here equals 0. Well, what do you know? Look what you get now. A squared equals b squared plus c squared. And then this whole term now is going to turn out to equal 0 because it's going to be 0 times b times c times 2. So really you just get this. But that's Pythagorean theorem. So what does that mean? It means that if you're going to go to Triangle Island, you do not need to bring Pythagorean theorem with you. You can cross it off your list because Pythagorean theorem is just a special case of the law of cosines. Okay, so you can sort of just travel with the law of cosines, and you'd be okay. You'd come to any triangle, you'd be able to do what you need to do. It happened to be a 90-degree triangle, you'd plug it in, it would reduce to the law, to Pythagorean theorem. Okay? All right. So let's talk about proving some of these things. All right, we're not at Triangle Island anymore. We're just going to talk about two pretty famous theorems. Let's start with Pythagorean theorem. A squared plus b squared equals c squared. And the goal here is going to be to prove Pythagorean theorem. Come up with an argument why this must be true. All right? So to do that, I'm going to draw this picture. Here's one proof. There's many ways to prove this, by the way. So we're going to pick this one. This is sort of a famous one. We're going to start with a square. And what we're going to do is, notice in a square, what do we know? We know that there are right angles in all the corners, for example. So that's pretty promising. We know Pythagorean theorem only works in right triangles. I don't see any triangles yet, so I'm going to construct a few things. I'm going to go along a certain distance along the side here. I'm going to call that B. And I'm going to call the remainder of that distance A. I'm going to take this idea and do it to every side. So here I am. Here's B again. And there's A. And then here's B again. And there's A. And all these A's and B's are the same length. B and A. Right? Okay. So what I've done is I've gone from each corner at distance B along the side, called the remainder of the side A. And what I'm going to do now is I'm going to construct this new shape inside the square. Okay? All right, so let's talk about this new shape. We need to come up with something about it and figure out what we know, right? So let's think about this for a second. I'd like to know what kind of shape this is on the inside. That's my goal. Okay? I'm claiming it's a square, so we're going to come up with some reason why that's the case. All right. Well, if we think about it this way, let's name some angles. Let's pretend for a minute this angle up here is x. Then we know that this angle has to be 90 minus x. So then all these triangles, this is x, this is 90 minus x. Here's x, here's 90 minus x, here's x, here's 90 minus x. All right, so now the question is, what are the angles in here? What's that angle right there? Let's see if we can figure that out. So this angle in here, we could get that if we wanted to by doing 180 minus x plus 90 minus x. The sum of these other two angles plus this angle that I'm looking for would equal 180. Well, if you do that subtraction, you get 90. Well, that's very promising. That means this is 90, this is 90, and this is 90. Okay. Now, what do we know? We know we have a shape with a four-sided shape with four 90-degree angles. Question you ask yourself then, does that guarantee that it's a square? We're looking for a way now to convince ourselves that all these sides have the same length, right? And it's so tempting to try and use Pythagorean theorem because you would say, hey, wait a minute, look, a squared plus b squared would equal this side squared. And then over here you have a squared plus b squared, so these would have to be the same. But then you're using Pythagorean theorem to prove Pythagorean theorem. That doesn't make any sense. All right, when you do a mathematical proof, this is the statement we're trying to arrive at. So I can't utilize that during the proof. I have to, at the end of my set of reasoning, my sets of statements and so forth, arrive at that, at this thing. This is a goal here. But what can we say? We can say that each of these triangles here are congruent. And how do you know? By side, angle, side. Look, side, angle, side. You have the side A, a 90-degree angle, and a side. Over here, side, angle, side. Again, you have the side A, a right angle, and the side B. Side, angle, side, and side, angle, side. So all four of these triangles are congruent. And if that's the case, then you remember corresponding parts of congruent triangles are congruent from geometry proofs. If they're congruent, it means that all their matching sides are congruent. So therefore, all these hypotenuses, or hypoteni, however you say it, are congruent. So now we know that thing in the middle is a square. That's great. So now I'm going to name that thing carefully. I'm going to name the sides of it. I'm going to say that this distance here is C, and that distance there is C. I'm choosing the letter C. I might as well. Okay. Now we're hoping for Pythagorean theorem. So what can we do? Well, I'm going to start by asking you to think about the area of the inner square. So the area of that inner square there, because of the way we've labeled it, would be C squared. We know that because it has, a length and width that's both C. All right. Let's also start to think about the area of the, or I should say area of any of those triangles. Any one of the triangles. Well, area of a triangle is 1/2 base times height. In this case, like if we look at this triangle down here at the bottom, it looks like 1/2 AB. That's what it looks like. 1/2 the base times the height. Okay, so far so good. And then lastly, I think you can come up with an expression for the area of the large outer square. Let's think about that for a minute. Take a look at the picture. So if we look, the length of the whole side of this square is A plus B. So that means this expression has to be A plus B squared. Okay. So you might be thinking, oh, what does this have to do with Pythagorean theorem? You're talking about areas now. Well, what do I know? I know that the area of the inner square, this area in here, plus the area of all four triangles altogether would equal the area of the big square. So now I'm going to write a statement. Here we go. C squared plus 4 of the little triangles has to equal A plus B squared. Okay. Let's start doing a little bit of math and see what happens. We'll have C squared plus 2AB equals, be careful with this is A plus B times A plus B. Well, that's A squared plus 2AB plus B squared. These cancel, and what do you know? Now, isn't that exciting? So we got it. There's Pythagorean theorem. All right. So let's go to the law of cosines now. Because the law of cosines can be proved also. That's what we're going to do next. Okay. So let's take a look. Here's how we're going to start. We know where we're going to end up. We're going to start with a triangle. Now, we're not starting with a right triangle. Law of cosines doesn't say anything about the triangle having to be a right triangle. So we're just starting with a general triangle. Labeling the sides here. There we go. Okay, so this is just going to be a little bit of algebra manipulation and so forth. It'll seem a little dark for a while, and then all of a sudden we'll discover our theorem. Okay, so first thing we're going to do is we're going to draw an altitude into this triangle. Now, I don't know how tall this is. I'm going to call it H. Okay. All right, so let's see what relationships hold true. Now, if this is h, when h comes down, this height comes down and intersects the base, it breaks the base into two pieces. So let's say we call this side x, then we have a pretty good name for the other side. Okay, yeah, a minus x would be a good name for this side because we know the whole length of that side was a, and then this section of it was x long, so a minus x is left. Okay, so let's see what we can do. Let's start writing down some statements that are true. Now, we just proved Pythagorean theorem, so we can use Pythagorean theorem here if we want, right? So what sort of statements can we write that are true? We could write this. X squared plus h squared equals b squared. We can write that because of the right triangle that's right here. There you go. Okay. So let's see what else we can write. Okay. We also have this fact. If we take the triangle that's on the left, on the right that is, this guy over here, we can write a minus x squared plus h squared equals c squared. Okay then. Now, you have two equations in front of you, and if we count them up, we have x, h, b, and a, and c. So we have more variables than equations. So we know that's kind of a problem. We can't solve for all five of these things. Five of these things, yeah. So, but what can we do? We notice that they have h squared in common. So let's take this equation and rewrite it. I'm going to write this as h squared equals b squared minus x squared. And what that means now is that I can actually sub that into this other equation, because that equation is x squared also. So if I do that, follow the arrows here, we end up with a minus x quantity squared plus b squared minus x squared equals c squared. Okay. So let's just do a little bit of algebra. This is one of those times where you sort of think to yourself, where are we going, right? You're not quite sure. You don't see law of cosines coming to us anytime soon. So we're just going to sort of see what happens. All right, so if we square this out, we get a squared minus 2ax plus x squared, right? All right, so what do we have? Plus b squared minus x squared equals c squared. And oh, wow, I see something. Look at this. These are gone. All right, so far, so good. We have a squared minus 2ax plus b squared equals c squared. And my claim is there might be a little bit of light at the end of the tunnel. You might be able to see something here because this almost is beginning to look like law of cosines, even though cosine is not anywhere in the expression. Let me reorder it for you so you can see that. A squared plus b squared minus 2ax equals c squared. All right, if you look at it, it's starting off just like law of cosines. This part looks great. And then it's minus 2 times something. And here's one of the sides, a. And what's missing is what should be here. Now we know what we're hoping for. What we're hoping for is b cosine big C. That's what we're hoping for. Then it would look just like the law of cosines. Right? So that x is really I got to get that out of there somehow. Let's go back to the picture and study it a little bit and see if we can't resolve this issue. So here we go. Here's x in the picture. Now I'm looking at x because I know that's what I want to get rid of. I don't want x in my expression anymore. So let's see if I can write anything that has x and cosine in it. So here we go. Ready? Cosine of big angle C would be the adjacent x over the hypotenuse B. You can see that in the blue right triangle. Here's the blue right triangle. If you look at that, here's the cosine of angle C, here's angle C. So the cosine angle C would be adjacent, which would be the side x over hypotenuse, which would be B. But that means that x equals b cosine big C. That's exactly what we're hoping for. So we have it. A squared plus b squared minus 2a. And instead of writing x, I'm going to write what it equals, which is b cosine big C equals c squared. And now we have the law of cosine.